Hello and welcome to another video from the PowerPoint series from movingelectrons.com. Our topic for today is going to be protection coordination. Again, a very interesting topic. If you talk to experienced protection engineers, they will tell you this is probably one of the only fields in electrical engineering which can be considered half science and half art. And we'll see why that is. Our focus for today in this very wide topic is going to be zones of protection. Before we get into the details though, let's read our question. In the system below, the primary protection zones are shown. So these are the primary protection zones. If a fault occurs at point F, which breakers will trip? And this is where our fault is occurring. So we have different protection zones here. We have the generator, and these are only primary protection as it's mentioned. We'll talk about that in a bit. What primary protection is, what secondary protection is. So there's generator protection, there is the bus protection zones, all of these. There are two transformers, so there's the transformer protection zones, and then there are the line protection zones. And these are all breakers in there. So this is the location of our fault right here. That's fault F. We've been asked to see which of these breakers would trip. Would it be the upstream breaker, breaker 3, the downstream breaker 4? Would it be a combination? Would it be 3 and 4 both? Or would it be 2, 3, 4 and 5? And let's get into the details a little bit. What I want to start off with is focusing on where coordination fits in a relaying protection system. So for that, let's look at what are some of the main objectives. What are the main objectives of a protection system? So one of the very first things that when you're designing a protection system you want to do is you want to make it selective. So it's selectivity, and that's where coordination fits in. So selectivity is basically the ability of a protection system to not only detect but operate only for the faulty part of the circuit and not for the remaining part of the circuit. So if there's a fault in the generator or there's a fault in the transformer, you just want the protection for the transformer to operate, not the one for the generator to operate as well. So selectivity is the ability to detect and operate only on faulty part of the circuit. So that's one of the primary objectives when you're designing a protection system. What's the next one? So we've learned about coordination. Coordination fits in right there, but there are lots of other objectives as well. So there's speed. You want your protection system to operate in a timely fashion such that one, or let's say A, you don't damage the equipment from the fault condition. So prevent damage of equipment. B, you prevent under voltages. That's a V, that's a U. So prevent under voltages due to fault conditions, and you prevent another fault from developing. So if there's an existing line to ground fault, you want to clear that fault before another line goes to ground and you have a double line to ground fault. So there's selectivity, there is speed, there is sensitivity. So you want your system to be sensitive enough to differentiate between what's a faulty condition and what's not. So you want it to be, for example, highly sensitive to fault conditions, but you want it to be insensitive to load currents. So for example, when you're designing the motor protection, you want the inrush to go through the breaker or the motor protection, but you do not want a fault. You want it to operate in fault conditions. So you want it to be able to differentiate whether it's an inrush current or it's a fault current. So you want your system to be sensitive. And then you obviously want reliability. That's kind of self-explanatory. You want it to operate as it's programmed or as it's designed. So you want your system to be reliable. You want your system to be simple. So when we say simple, the design of that should be simple, keeping in mind that the system has to not only just be, it's not just a design on paper, it needs to be physically installed. You should be able to test and commission it. You should be able to, the operators, because once the construction team's gone away, the operator should be able to operate and understand your design, and you should be able to maintain your system. So all of these need to be kept in mind when you make a system protection system simple enough. And then lastly, you want it to be an economical system. So you have economical constraints to be met. For example, you can make a system maybe extremely simple, but it's not economical because you'll need X number of breakers or X number of protection devices. On the other hand, you could make it very selective and very fast, but once again, it might not be economical and also might not be simple to operate and maintain. So you have to make sure these are some of these objectives are divergent. Not all of them meet each other. So that's one of the reasons, as I mentioned at the beginning, a lot of engineers consider this to be half art, half science, because every protection engineer would design their system a little bit differently. But the main thing is they should meet all these objectives, and it should be able to protect the system and any personnel that are operating that system. So we've gone through these, and one other thing that I wanted to bring your attention to, which we spoke about in the question itself, and that relates to that. So these are, so as I mentioned, coordination amongst all the objectives that we have, coordination fits in selectivity. This is where coordination fits in. And then when you're designing or you're coordinating a system, you have your primary zone of protection versus your secondary zone of protection, secondary or backup zone. So for example, if you have a radial system, let's say, and you have a breaker here, a main breaker comes down here, and then you have X number of feeders connected to various different loads. If there's a fault that happens here, your primary zone of protection should be these breakers. If there's a fault on any of, in case of this fault, then this is your primary zone of protection. But what I mean to say is, if there's a fault on any of the feeders, it's the feeder breakers that are your primary zone of protection. So you will coordinate this breaker with the upstream breaker. For example, for a particular fault current, you might want to operate this at 0.5 seconds. And then for the same fault current, you might want this breaker to operate at 1 second. Obviously, if this operates, you're isolating only this feeder, and your rest of your feeders can continue to operate. If this fails, then you have your secondary zone, your backup zone of protection, in which case a larger portion of your protection of your power system would have to be non-operational. So therefore, it's important that primary zones of protection work and are designed properly. And coming back now to our question, if these are the primary zones, then what we've been asked to find out is, if a fault occurs on the bus here, which of the breakers would operate? The idea generally is that so this is the primary zone of protection. So any breakers in that primary zone of protection where the fault occurs would open. So in this case, it would be both breakers 3 and 4. So our answer is B right here. It won't just be the upstream breaker, because if your upstream breaker opens, yes, the source, the generator is not feeding into the fault. But what if there's a motor feeding into the fault? So you want both your upstream and downstream breakers opening up. Coming back to the concept of primary zone versus secondary zone. So if this is the primary zone, we haven't marked the secondary zones here, but let's just think about it, what the secondary zones would be. If breaker 3, for example, fails to operate, you would want breaker 2 to open up. So for a fault here, I would imagine breakers 2 and 5 to be part of the secondary zone scheme. So if either 3 or 4 or both of them fail to open, then either 2 or 5 or both of them should open in that case to isolate this fault. So that's what I just wanted to focus on today. Hopefully you got a brief idea of what our main objectives when you're designing a protection system are. Hopefully in future videos I'll go in detail of some other topics that we've spoken about here as well. Also, I hope you got an idea of what protection of what primary versus secondary zone is, what the difference between them is, and how to solve a question of this kind if it's asked. One thing I should mention, in this case the fault here happens only in one primary zone. What you also notice here is there are some overlapping primary zones. So for example, here the transformer protection doesn't stop here, it goes all the way till here, till almost the bus, but just stops before the bus. Because if your primary protections were just set like this, then there would be some gaps, and therefore there is always some overlap. Now what happens in an overlap scenario? What if our fault, instead of being here, was here? So it would fall in both the primary zone, this one, as well as the line protection primary zone. So in that case you would have breakers 3, 4 and 5 open up because it was in an overlapping zone. So any breakers in this zone, in the bus protection zone, as well as in the line protection zone would open up. So I hope that's clear. I will give you a sample question as well. So let me show you something here. I've already drawn this one out. So let's see. Again, so in this case we have two parallel generators. There is no tiebreaker here, but there's a tiebreaker here at the secondary of the transformers. And let's say our fault occurs here. So that's your point F. In this case, which breakers would open? Would it be 3, 4 and 9? Would it be 7, 8 and 9? Could it be just breaker 9? Or would it be all of these breakers? Think about that based on the discussion we've had. And I look forward to your answers in the comment section below, as well as any comments that you might have, any feedback that you might have. If you have any questions, you can even send me an email, nimish@movingelectrons.com. So till next time, take care and have fun.